Hi again, Calc AB students. Mr. Ray here again. No, I did not wear the same outfit 2 days in a row. I'm recording this just after the previous video you just watched. I'm trying to get them both done so that Ms. Hoagie and I can take a look at them and see if we like them or if we just want to call them garbage and we'll throw them out. So if I'm not wearing the same thing, you wouldn't even know. So don't worry about it. Anyway, last time we met, we were talking about functions, some of this pre-calculus mathematics that we were just kind of reviewing, some of the higher highlights from your previous few years of math, just that those things are going to come in pretty handy if we have them sort of at the ready mentally as we get ready for our journey through the land that is calculus. It does hit everything along the way, and so we'll be putting a lot of those skills to the test. So last time we met, we talked about classes of functions, and we looked a little bit at like the different kinds of functions we'd seen before, reviewed the idea of intercepts, and also got into the linear functions a little bit more in depth. So I think if you take calculus and you look at all the different complexity of functions that we deal with, the idea is we try to simplify them as much as possible, and linear is pretty good, and we like to use those linear functions whenever we can, and that'll be something coming up for you a little bit later, that if we can take what was a sort of complex function and reduce it into something linear, it does get a lot easier. And that's something that Newton and Euler and a lot of the other mathematicians of the day were really trying to do a lot of. So today, for day 2 of our pre-calculus review, and really the only other day of our pre-calculus review, we got to get into this stuff next week. We're looking at a little bit more about functions and their graphs, and the idea that there are things that we can look for in functions that give them some structure so that we can understand when we change things within those structures, how that affects the graph of the function. And so we'll be looking at how to shift a graph, either up and down or left and right on the Cartesian coordinate plane. We'll also be looking at domain and range a little bit more. And we'll address the idea of, is everything we deal with a function, or is there some other thing out there? And you probably already remember that there was something called relations that aren't functions. And how do we know? And what does that do? What does that do for us when we figure that out? So we're going to go back to my on-screen whiteboard here, and then I can highlight a few of these things for you a little differently. So the first thing I just want to touch on are functions and their graphs. And specifically, I want to get into the difference between a function and a relation, and then what happens when we start looking at the structure of the functions and determine whether or not those are what the graph's going to do when we make different changes to the structure within that function. So let's see here. We want to talk about functions. Versus a relation. And we're going to compare and contrast these a little bit. For a function, something that is the same here, they both have a domain and a range. Domain and range. Domain and range. They both have that. They could both have intercepts. X and Y intercepts are things that we might be interested in. Same thing here. X and Y intercepts are things that we might be interested in. They don't always have them. Okay, that's true. Okay, that's true for both of them. So the big difference here, or the main difference, is that in a function, every element in the domain, okay, so the x's, goes to a single element in the range. So for each x, in the domain okay, there is one y that's in the range. Oh no, my pen got all crazy on me there. Come on. So what we mean is, if you take f of x, it only goes to one place in the domain. The big difference then is that in a relation that it doesn't have to be true. It is possible in a relation for x to lead to multiple places in the domain. In I think it's probably your Algebra 2 year, when you first kind of started to develop this idea, you probably learned something called the vertical line test. And so graphically, the illustration goes something like this. If I have my x and y axis, okay, and I draw my function on there, and my function has no place where I can draw a vertical line and hit more than one part of the graph, then it is a function. Okay, you can see, because for each x along the x-axis here, the graph has exactly one y coordinate. Now, it doesn't mean there's not more than one way to get to a certain y coordinate, of course. But you could just look at a parabola, the basic parabola, and go, oh, look, positive 3 gives you 9, so does negative 3. But that doesn't matter. What matters is that positive 3 can only lead to one place. Okay. The difference is in a relation, we don't have this restriction. Okay. In a relation, and maybe if you think back to your Algebra 2 days, you probably saw some conic sections, specifically a parabola, and you saw some parabolas that went this direction. And notice even the y-axis is a nice use of the vertical line test. It has more than one spot. And so this is not a function. Whereas this is a function over here. This one was a function. Okay. The fun thing is in calculus, we're going to deal with both. So yes, a lot of our calculus will be dealing with functions. That's true. But there will come a time in calculus when we are dealing with relations. And when we get to that point, you're going to see why the difference is pretty profound for us. So it's very important for us to know whether we're dealing with a function or a relation. And the way we tell is this vertical line test, or to look and see, is it possible that one x value might lead to more than one y value? In the parlance of mathematics, does each value in the domain lead to a single point in the range? And so that was the definition for a function. All right. I think I had mentioned earlier that we were going to talk a little bit about seeing some structure in functions. And specifically, I wanted to talk about how do we look at shifts in the graph when we get ready to make the graph. So this is shifts in the graph of f of x. All right. So by structure, I mean, we're going to take a look at our function and like so. And what happens if I take a look at that function, I realize that maybe all I've done for another problem is taken that original function and just added a constant or subtracted a constant to it. So if I add or subtract some constant c, what happens? Okay, and I'm going to use the specific example of a square root. So over here, I'm going to define my function y equals the square root of x. Now, for those of you who remember back to your pre-calculus and algebra 2 days, you probably, oh, I didn't mean for that to be red. Oh, shoot. I can't. Can I change the color right now? No, darn it. All right, we'll get rid of it. And then we'll change the color for this one. Because I want to keep the graph red. And then its corresponding changes are going to be different colors. So it's kind of a fun trick. So you might remember the square root of x looks something like this. Okay, and so by adding or subtracting a constant, okay, so plus or minus some constant here, what happens to the graph? If I just change my function a little bit, can I take advantage of the structure of that function? Well, sure, because I know that by subtracting 2, what really happens is it just takes all my y coordinates, my range values, and decreases them by 2. It has no effect on the shape of my function. And so you can see, all I would do would be moving my graph down 2 places. Similarly, if I added 2 to my function, it would raise it 2 places, but I would not be changing the shape of my function. So by adding or subtracting a constant outside of the function itself, I would create what's called a vertical shift. Let's see. What if we add or subtract inside of our function? In other words, so the addition or subtraction happens inside the function. Well, similar idea in that the shape of our original function won't change. Okay, these transformations, these shifts in their graphs doesn't really change the original shape of the function. It's really just going to change the location. So if I do this, let's say y equals the square root of x minus 2 inside that function, okay, that's going to create a different shift. Now, the interesting thing here is I want you to notice that the original graph, the red graph, has this point at the origin where the x coordinate is 0. So what has happened by subtracting 2 here from that 0 point, okay, in order to get back to 0, what would x have to be? It would have to be positive 2, wouldn't it? And that's exactly the shift that has happened in my function. I've moved all the x coordinates to the right 2 places. Okay, and the way to sort of figure that out or to think about it is, okay, my original square root was square root of 0 when if I started at 0. Well, how would I get back to 0? Oh, if x was positive 2. So it has to be going through the point 2, 0. I think I mentioned in the previous video how those intercepts are oftentimes really important points for us. Well, here's another great example of that. So as you just saw, some structure. If we understand the structure of this function, we can see that a function that is closed with a constant added outside of the function will result in a vertical shift. A function that has the constant added or subtracted inside the function will create a horizontal shift. The trick there is to remember, how do I get back to 0? That's going to be positive 2. So this is a positive 2 shift, or a shift to the right, even though it was minus 2 on the inside of the function. The last thing I wanted to look at was how do we create a reflection of our function? And oops, there's a little button on the side of my pen, and sometimes I click it on accident. There are 3 kinds of reflections we're going to look at. And you can see that, I think you can see pretty easily what this first one will do. If you just put a negative in front of your function, what happens is, of course, it just reflects it across the x-axis. So it would come down here like so. Okay. If you negate everything inside the function, okay, for us in this function, you have to remember that, oh my, we can't square root a negative number in the real number world. Okay, I should put a little caveat in there that we are only going to do calculus in real numbers. Okay, we're not going to invoke complex numbers in our study of calculus this year. Yeah, if you want that, you're going to have to wait a little while. Wait till you get to college and let some more calculus happen before you try that. So for us, then, if we do that, the only way that this would work would be if all of the x's that we were square rooting were negative already, because then they would turn into positive. So obviously that's a shift over the y-axis. I didn't draw that very well. Let me try again. Yeah, well, not much better. No faulting the instructor for bad artistic abilities with this trackpad, okay? And then the last one, this double negative here is just going to be both, right? So it's flipping it over the x-axis and over the y-axis. And what I think you'll see is that it actually results in a 180-degree rotation around the origin, which is pretty cool. So if I take a look at my red function and I apply both the negative on the outside and the negative on the inside, the result is a function down here. So we have the double negative function, which you can kind of picture in your mind, that red arrow kind of rotating 180 degrees around the axis. I'm sure there's some cool way to do that on this whiteboard. I just don't know what it is, guys. I apologize for that. It's not something that I've practiced here. So. All right, I think we're just about out of time here, so I'm going to stop this recording. If I have more time, then I will add a little bit about composite functions, but I have to check my time here. My timer, for some reason, got shut off. So thank you guys for your patience, and maybe I'll see you in a sec for some composite functions.